So good evening to everyone. I'm Riccardo. Today we're going to talk about multi-scale node embeddings for graph modeling and generation, and focus on the first three words. We will track them down in this presentation. So start with node. What is a node? The starting point of defining what is a node is to define what is a network. So a network is a set of nodes and edges. And generally, they have defined towards those calligraphic G, so a tuple of V vertices and E edges. And usually, you assume the nodes to be fixed. So every person in a social network or inside the economy, a firm inside the economy or a sector inside an economy is known. What it is unknown are the connection among these entities. So one wants to have a probabilistic model to describe the interaction among the two entities. So to represent this kind of mathematical object, there is this famous graphical representation where three nodes are interacting here, but it is inefficient if one wants to have numerical computation out of it. So we can describe the interaction among entities with a mathematical representation, so a matrix. And since we will discuss only undirected applications, we have a symmetric matrix where, for example, the entry 1, 2 represents the connection among the two entities 1, 2, and it is reciprocated. So one has a 1 also in the entry 2, 1. To model this kind of 0, 1 phenomenon, you assume that the edges are independent Bernoulli random variable, but not identically distributed. So what do I mean by that is that Aij is the random variable that can be 1 with the probability Pij, that will be our model, and 0 with the probability 1 minus Pij. So for every connection, or either 0 or 1, you have a Pij. Okay, so I went back. Okay, so why node embeddings? Node embeddings are really useful because you have to think about the adjacency matrix involving all the pairs, either active or inactive, to be a really big matrix. And if you input this matrix into machine learning techniques, it will be unmanageable by the computational limitation. So the users are relying on a shrinked but rich representation. So if you have an adjacency matrix having n rows and n columns, then you rely on node embeddings that are that are of dimension n by d, where d is the dimension of the vector. And so you will have n vectors, every one d-dimensional. So with this shrink but rich representation, then you can do node classification, community detection, link prediction, and so on and so forth. So these kind of methods are really much in the literature that recently has been published a zoo guide to really travel around these kind of methods. So okay, so the node embedding procedure is a procedure where you start from the full observed network, and then you encode the role of each node into some latent vector space. Here we are in R2, so the encoder part is to attach for every colored circle that you have on the left, a rich representation, so a two-dimensional vector. How can you do that? You start from initial conditions for these parameters, and then you decode it back via your network model, and then you take a functional and you do this back and forth procedure to have the optimal vectors in your model. Okay, so the first word of my title was multi-scale node embeddings. So how multi-scales are emerging. So here we have a paradigmatic example. You start from the left, you have one generative ground truth. So, for example, the economic god that is having two sectors to exchange money, that is represented at level 0, 1, 2, and 3. And how these multi-scales emerges? They emerge from a human limitation. So at level 0, you have the classification of sectors providing us full service restaurant and limited service restaurant. So exchanging money with the hydrodynamical power generator. Okay, so at level 1, there is a coarser definition of sector where the two kind of restaurants were merged into one single sector identifying a restaurant. And now hydrodynamical power generator is merged with a fossil, for example, power generator in the electrical power generators. So you have level 1. You can also coarse grain the definition of the sectors at level 2, 3, and so on and so forth. Okay, so far we have discussed how the identification of sectors can lead to coarser and coarser communities, but we didn't specify how to connect those communities because a graph is a tuple of vertices and edges. So we assume that two communities are in contact if at least one micromember was in contact with another micromember of the other community. So this is a crucial assumption that we are doing. So the moral of this slide is that there is one God generating every kind of phenomenon that we are studying, but because of multiple specification of what a node is in that network, we can have multiple users to study either level 0 or level 2. And our model has to be 1 for every level. So we want to have one model to describe every level because there was one ground truth at work. But we will see this concept more in detail in few slides. So how node embedding relate in this multi-scale scenario? So on the left, we have the standard procedure of node embedding. You start from the observed network, you do the back and forth procedure that we have seen at the beginning. Then we have also discussed about that we can coarse grain the network because there are specification of merging the nodes, here the red nodes into the big block node. And one is tempted to do the same encoder-decoder procedure that we have done to have parameters for our model. But in general, how the microscopic node vectors relate with the macroscopic one. So the big red question mark is because in general, you don't have a model that is capable of describing how to go from micro to macro. But with our model, so the multi-scale model, we can just take the microscopic vectors, then use the parallelogram rule and ending up having the node embeddings for the community red. And we didn't refeed the model at this level. We just sum the vectors. So going further, this is the slide that usually came after 2 or 3 slides, but we needed concepts. So the motivations are to see and inspect the limitations of single scale models. And we will introduce the concept of single scale overfitting. Then we want to enhance the scalar multi-scale model proposed by Lalli and colleagues with node embeddings. Then we want to show the performance of the multi-scale model fitted only at level 0, and then give an interpretation of the sum of node vectors. Okay, so to recap, we have the full network, we do back and forth, and we end up having the node vectors. Okay, so the straightforward comparison is that since we have a bunch of zeros and ones, because we have seen the matrix representation of a network composed by zeros and ones, one is tempted to take the logistic function and to use the spam-non-spam algorithms to classify either if an edge is active or inactive. So the logistic PCA is a model obtained by maximizing the Shannon entropy, while in contrast, our multi-scale model is driven by the enforcing of the scale invariant principle. So forgetting about the maximum Shannon entropy, this information principle, but we want only to solve for the scale invariant principle. So we end up having this Pij, which is a kind of cumulative distribution for a Poisson process, and we had to specify that the vectors, so the community vector xi, is the summation of the microscopic vectors that we have obtained at level 0. Okay, so the pipeline starts by fitting the node embeddings either for LPCA, but also for our model. So we end up having those arrows. And at this stage, the Shannon entropy principle provides a model that is slightly better performing than the multi-scale one. While we go and we want to then extrapolate our model for higher levels. So the multiscale model prescribes to exactly sum the vectors, and we will do the same for the logistic PCA because it is a non-renormalizable model. So there is no recipe to take the vectors and create the bigger vector. So we want to test this logistic PCA with this kind of rule, even if we know that it will fail, but we want to test it. And then we reinsert them into the same model. So the logistic PCA has to have this functional form, while for the multiscale model, this functional form is enforced by the scale invariant principle. So the model is not changing any phase. It will mimic the ground truth, so the one generative process that was at work, and we can see the results here. As an interlude, I want to specify how this concept of applying a non-multiscale model to multiple scales work. So you have your fancy neural network, you want to describe the economy at level 0, and you then end up having this plain set of parameters. Okay, then another practitioner comes to you and say, okay, I have the same process, but at level 1, how you do with a neural network? You have to refeed it. And if you refeed it, you will end up having this struct set of parameters. And from a neural network perspective, it is as if the neural network has fitted an economic network at first, but the second one completely independent network. So you don't have any relationship on these parameters, even if you created artificially this L1 by considering partitions of the nodes at level 0. So you have to refeed your neural network at every level. While with our model, we fit once and then we sum the vectors. And we can consistently have this statistical consistency on our parameters. Okay, so cross comparison among the models. Here we have on the x-axis level 0, 1, 2, and 3. And so finest sector to sector level, and then coarse grain, and coarse grain. On the y-axis, we have the sign relative error, which means the difference of the expected number of links minus the total number of links divided the observed number of links at each level. We fit it at level 0, so here all the models are capable of replicating the total number of links. Well, if we release the scale, we have that LPCA underestimates really abruptly this kind of measurement, while the other multiscale models are staying up. So with a minimum disagreement with the total number of links, but you can recover just summing the vectors, the total number of links. Now, since we are speaking about machine learning, we have provided here AUC-ROC and AUC-PR. We can see that LPCA slightly wins at level 0 where it was fitted, but then you have that LPCA degrades as soon as the level is released. So we have consistency for the multiscale models, and we are happy with that because we wanted to have consistency for every level. And it is really important, one thing to remind is that we solved for the scale invariant principle, which is only an humble requirement of inner consistency of the model. We didn't require that for every partition that one user can use, the model should mimic the refitted counterparts. So we can have deeper insight into the scale invariant principle, but we are not requiring that for the communities that will be generated, then the model will replicate the connection on those communities. But for every partition, even a random one, you can use the same pipeline. Okay, so the conclusions here are that we used a multiscale model, which is not a Shannon entropy model, but it is a scale invariant model. LPCA must be refitted at every level, but every non-renormalizable model should be refitted at every level. We have seen that at level 0, LPCA was doing a better job than multiscale model, but not so much. While changing scale, it will be really multiscale model that outperformed the other. We have seen that we can interpret the sum of multiscale vectors because now we know that that vector, it is the community one, and the future perspectives are saying that if we assume that there is not a model for every edge, but we say we can do train and test splitting, it means that the test edges will be, so the assumption is the test edges are distributed as the train set. Then we can do this train and test splitting and do link prediction at with the directed model, which is encoding one embedding more. And actually, I've done this exercise. So random split is 70%, training 70%, test on 30%, coarse grain at 2 levels with the 30% of unseen edges. And we have disagreement for the number of neighbors. Okay, so thank you, and I'm open for questions.
Thank you, Riccardo. Any questions?
I want to understand on which types of networks you apply this experiment and whether the approach is kind of application dependent or is expected to behave well in any kind of graphs.
So we were really only maximizing the likelihood for every. So you need to have the full network, either splitted in train and test or just only train, and then you plug in your 1 and 0, and you can retrieve your model. We didn't assume anything. So it is really these 2 steps. You have this model, you plug in into this, and that's it.
Yeah, but in terms of application domains, I mean.
So it's a network-based approach. So every phenomenon that could be described in a dyadic interaction with entities and a bars connecting them, and then.
Yeah, but the experiments you performed were on what
sector to sector. Yes, if you want the data set. So the limitations are none. What I've been doing is to study this data set. So I went to ING.
From network.
It's actually a sector-to-sector production network. So we went to ING. We asked access to the ING data. We selected the year 2022. We remove at the firm-to-firm level self loops because of accounting payments. Then non-ING partners, because ING was interested into ING. The non-Dutch payers and beneficiaries. The one without a grid ID, which is an identifier for big clients, and we remove the individuals because of GDPR. Then, to obtain a production network, we remove the public administration because of taxes, the finance and insurance because they are not providing a unique product, but also loans, and management of companies and enterprising, so the holdings. So an holding can hold many other firms inside. And so we removed this kind of sector. Then we aggregated this filtered firm-to-firm by NICE code 6 digits to have this sector-to-sector production network. Then we also binarize in this way the network, and we reciprocated every edge because the model that was in the literature was an undirected one, but without so much effort, you can describe the directed interaction by promoting one parameter x to be y. So I mean, instead of pij 1 minus e to the minus xi xj, you encode the second x, so xi yj, saying that the first xi is the propensity of generating of an outgoing connection, while yj an incoming connection. And you can do that. I've shown that you can do that, and you can have also really good coarse-grained results, which are the one that I've shown you as an exercise. I went. Okay, this one. So I've done that kind of reasoning.
I will go on. Thank you, Riccardo.